Okay, we will start our WebEx session. My recording session is started over here. So homework 6 is due Monday. For the sake of the students going on the tour tomorrow to OSI, everybody has the weekend to finish that homework assignment. If you're having any trouble with any of the code, let me know. I want to encourage you to, if you should have downloaded it. I would encourage you to download it. If you haven't downloaded it this week, if you downloaded it a couple weeks ago, I'd say delete the MATLAB files, the directories, and the zip file, and reacquire it, download it again. I did do some updates and corrected some problems on it, so it should be working okay for you. Okay, I want to just do a little bit of review from last time. We talked about the security constrained OPF, SCOPF. Again, it has constraints on line flow and constraints on line flow with an outage. In other words, I'm going to set the system up sort of pre-arming it so that if there's an outage, nothing overloads. Now remember, that's the NERC N-1 criteria, that no line will overload on a single outage. And what we're doing with the SCOPF is we're pre-dispatching. We're dispatching the system, given the load that it has and the generation units that are committed. Then I can schedule the generation and know that any single outage will not result in an overload. This is the way markets operate. If you just do economic dispatch, you get the least cost. If you put line flows in there, the economic dispatch might overload some lines. It shouldn't, because you probably didn't do a good job designing the transmission system. But if you have some difficulties, maybe there's some lines out for maintenance. Anyway, as soon as you put a line flow limit, the cost is going to go up. And as soon as you constrain it to not have any overloads with a contingency, the costs go up even more. So much of the time, those kind of constraints are active during peak loads. So, and this results, we will see later on, this results in LMPs. And you remember our little two-bus, my favorite little two-bus problem, where you had a load here, and you had a line, and you had a generator. Let me put the loads over here. And you remember that when it was, the line flow was limiting, the solution to the auction required that the LMP, the price at each bus was different. Well, if you have a network, then when you have a line flow limit or a contingency limit active, then groups of buses will be different, and in fact there will be sort of a gradation of costs, and we'll show that, and that's best illustrated with contour maps with colors for the the highest cost being red and the lowest cost being blue. They use temperature as an analogy there. In any event, so that's the purpose of the SCOPF. Now, we showed this with the DCOPF, with the so-called DCOPF or linear OPF that uses the linear model. Then we went into the AC OPF. Much harder problem. In fact, the DCOPF is frankly quite simple. You can use a linear program, you can use a quadratic program, and if you know how to set up the matrices as I showed you last time, you can build a DCOPF very quickly. ACOPF, I cannot tell you how many different engineers from different companies and different universities around the world applied themselves to come up with an ACOPF in this, what I call this 30-year period that it took to get decent ACOPF, and that occurred, fortunately for us in the late 1980s, early 1990s, and I showed you the one which was the iterative LP. That's a very and once you've decided to go that way, iterative LP, which means you linearize, you solve the LP, and then you solve an AC power flow, and then you relinearize, and then you come back like this, and you just keep going around. You relinearize, you solve the LP, you solve, when you get to a solution, you solve the AC power flow and relinearize until you cease to make any headway. That's a common optimization tool. I want to make sure. Yeah. So it's important that you understand that this was a hard problem. There's several. I shouldn't say several. There's probably hundreds of ways of varying the code, and people have devised all of them. Remember, I said that you get a really nonlinear function, and you're trying. Let's say you're trying to minimize, so you're coming down. Okay. And so you start out here, let's say, and you have some limits like this, and you have some transmission limits. But you do a little tiny window, and then that little tiny window, if we blow it up, and we linearize it, it looks like a little LP. We're starting on it, it's going to work its way over here, like that. Then we draw another one. Well, it can turn out, in order to move fast, you could make the window bigger. Let's suppose I did it in red over here. I said, look, I'm going to go with a big LP window like this. And I get down here. Boy, that worked very well. But then I do another one around that when I relinearize, and I get to a point where suddenly the next LP, the cost didn't go down, and it's kind of reached a place where maybe it's oscillating back and forth. Then what you want to do is you need to shrink the window. So you gotta bring the window size down. You gotta have, that's gotta be adaptive. And so you reduce the window, then the linearization doesn't change, but the amount of movement doesn't result in an error because you're moving on a nonlinear surface, but a smaller distance. Lots of techniques like that you can use. So today I'm gonna introduce a different technique, and we're gonna give you a homework problem and some MATLAB code to do this. But I'm gonna introduce one that's called the interior point, OPF code. The idea behind that, it seems simple. It seems real simple at first, but would that life was always that simple. Here's the idea, and that is that let's suppose that I've got a problem like this, and I've got a constraint that looks like this. So this is the constraint, and you can't, back here is not allowed. You can't go back here. So we'll put this crosshatch like it's a fence. So you got to stay in this area here. Well, you start doing the optimization, and I'm not doing it with LP now. I'm doing it with something else, and it says, oh look, I can create a gradient, and boom, I come down here. Well, wait a minute, you're now beyond the constraint. How do I force it back? And one of the very earliest optimization techniques said, well, we'll put a penalty. So let me look at this constraint. I'm going to draw, and I'm going to draw as if I'm looking at it here. So here's looking at it as if, and here's the constraint, and I'm going to be moving. Let's say this is my objective function. Well, any kind of gradient technique or Newton technique will take me beyond the constraint. So what I want to do then is I want to say, well, I'm going to add to the objective something that will cause the surface to look bent and go like this. So now the surface comes down and it bends up. So if I start doing an optimization and I'm coming down here with a Newton's, it's going to stop here. You can call it a penalty function. In the interior point, they call it a barrier function. That's the name that it received. Now, going back, there was a lot of work in linear programming over the years, and people said, gee, LP starts out and it goes jumping from one intersection to another to another to another along the constraints. That's the beauty of LP. And they said, let's make it move through the middle, so to speak, blast away right down through the middle to the optimum. Well, that required a lot of work, and there was a fellow named Karmarkar who worked out that methodology. Interior point is similar to that in that it allows you to optimize using what's called a Newton method, but it has this barrier function. And the people that worked that one out showed how to do a barrier function that would grow. So you can see with my little problem here that if it's solved here, there's still there's still a gap, right? There's still a gap over here, right here. You're not at the constraint. So that little penalty function is going to have to be, it's going to have to be more powerful. So here we're gonna go like this. We're going to make it more powerful. I can tell you that the problem with those kind of methodologies is that Newton's method will fail because it becomes unstable when it gets up to constraints like that. It simply won't work. I can say that out of experience. I tried it. It doesn't work. So what we're going to do is we're going to show you Newton's method, the most simple. I mean, Newton's method is like the Newton power flow. Newton's method is says, and you know Newton's method. Newton's method says I want to find f of x. I'm going to say f of x. I want to solve it for f of x equals 0. I'm going to solve. Let's see, f of x 0. That's fine. It solve for x 0. What is this that drives the whole function to 0? Nonlinear function. Nonlinear function of x. Just one variable is enough. So we build a Taylor's expansion. We say f of x is equal to f of x. Let me get rid of this 0. F of x star. Solve for x star, because f of x 0 is just my starting point. Okay. F of x 0 plus df dx times delta x equals 0. Now I've just said my nonlinear function over a small region that's fairly accurate is going to be a constant plus a linear function like this. Well, if that's the case, then I'm going to solve for delta x, and that is equal to minus df dx inverse times f of x0. So you just take this function, drop it over there. There's the minus sign, and you divide by this, and you get this. And then you say, okay, so x new or x1 is equal to x0 plus delta x, and then you go back and you say, okay, now I'm going to solve for delta x. A new delta x is f of x1 plus df dx times, delta x1 equals 0. And so you just do it again. Now, we should have set up here that the derivative is evaluated at x equals x0. You evaluate this at x equals x1. And so forth. You just keep doing that, and you're all familiar with, you've got some nonlinear function. You want to know that there's the solution. There's x star, and you're going to start here and you solve it, and here's the slope. Well, you get down to this point, and then you get the next value, and it'll iterate right down in very, very comfortably, and that is the way you do it with sets of equations. And again, I may put this in your homework too. Let's say I had f of x1 and x2. I had f1 of x1. I want that to equal 0. At the same time, I want this to equal 0. Well, when you expand this, you say, well, f of x1 of this is f of x1 of x1 0 and x2 0 plus df1 dx1 delta x1 plus df1 dx2 delta x2 equals 0, and f2 of x1 0 x2 0 plus df2 dx2 delta x1, let's keep them in order there, plus df2 dx2 delta x2 equals 0. So now I have two equations and I have two deltas, and it's best to put these into, here's f1 and f2 plus, and you just arrange this into a common dx1 df dx, this is f1 x2 df2 dx1 df2 dx2, Jacobian matrix delta x1 delta x2 equals 0. And you end up by solving this by saying delta x1, and delta x2 is equal to minus, and this matrix I'll just call J inverse times f1 of x1 0, x2 0, and f2 of x1 0, x2 0. So I can solve two equations simultaneously that way. Okay, now what has this got to do with optimization? Well, in optimization, the equations that you want to solve for are always involving driving optimize. You want to minimize some function, okay, and it's usually the sum of a bunch of nonlinear functions, f of x1, x2, and so forth. And so calculus says, well, find a point where the first derivatives are all 0. That's at least that's the first condition that you'd have for a minimum. But then there's other conditions, as you know, on the second derivatives, and otherwise it's just a flat spot, and it could be an inflection point. Blah blah blah. In using the interior point, you do this. You say, well, I'm gonna start out, and I'm gonna have f, and I'm gonna say that I'm gonna have this variable mu, and so I'm gonna designate this as f of mu is equal to my f of x, and this is a vector, so it's a multi-dimensional. This has many different variables in it, minus mu to the k, the sum of the natural log of s sub I equals 1 to the number of inequalities. N-I-N-E-Q up here. So this is N-I-N-E-Q. That's what that variable is. And you say, well, this is my my minimization function, and we're going to say, well, that there's some equality constraints. G of x equals 0, and there's other inequality constraints. H of x plus s, okay, equals 0. So h sub I of x, for I equals 1 to the number of inequalities. Now you remember, adding a slack variable is the means of forcing this equation to equal 0. If h has in other words, if h of x must be less than or equal to, let's say, some constant, or should I make it 0? Let me just put a some number here like 6. H of x must be less than or equal to 6. Well, then I'm going to say h of x plus s equals 6. Now, then I'm just going to say h of x minus 6 plus x equals 0. Now, when h of x, for example, is much less than 6, well, then this is a negative number, right? If h of x equals 3, well, then 3 minus is minus 3. Well, then you just say s is equal to 3 more to bring it up to 0. S fills the role as a slack. It takes up the slack. That's the way, the reason it got its name. And so this thing here has to do with forcing the equations into a solution, even though there's inequality constraints. Remember, for equality constraints, we got it made. We've got techniques to handle them. So now we form a Lagrangian, and we say it's f of x. This is a vector minus mu k natural log of si over I equals 1 to n I n e q plus lambda transpose g of x plus, and I'm going to put a gamma transpose times h of x plus s. And this is just the standard way of doing Lagrangian. This is our old Lagrangian method, okay, where we put a Lagrange multiplier times each equality constraint, and a Lagrange multiplier times each of the inequalities. As long as we've put a slack variable in there, we can treat it that way too. Now, this thing out here that I'll outline in red, that thing is there for a very special reason, and what we want to do, what we would like to do, is force the slack variables when an inequality is on its limit, so-called active constraint. Well, then the s is 0. So we want to drive the s to 0. And you'll notice, and what we do is we're going to play with the magnitude of this mu. We're going to play with the magnitude of mu. Now, so when we did economic dispatch before, remember we took dl and we took the derivative with respect to each variable in the equation. We do the same thing here. So we say dl dx, and we're going to give that a notation like that. Gamma x times L of mu. This, I should have a mu here. This is L of mu. That simply means to take the gradient, and that's just a vector of first derivatives, which is then equal to the gradient with respect to x of f of x plus, there's no x in this thing, so then it's the gradient with respect to x of this thing, and that turns out to be simply g of x times lambda, times lambda vector. The lambda was a vector transpose, it was a row vector, now it's a column vector. And then this becomes gamma of, or the del of, they call that del of h of x times gamma. And we say that's equal to 0. Now we're going to take all the derivatives with respect to lambda. So the gradient with respect to lambda of L of mu is equal to simply g of x. That's the lambda. The gradient with respect to the gammas, this is h of x plus s, and then the next one, we have a variable now called mu, so we're going to take the derivative with respect to that, and that's just going to give us h of x, I'm sorry, this one doesn't, plus s, and then the gradient with respect to s is simply equal to minus mu to the k, that's an exponent, times cap s in inverse times e plus gamma. Well, what is this? What's this s? Well, this s is simply all the slack variables in a matrix on the diagonal, and then e is simply the vector of ones. Okay. And now what we have to do is we have so many equations and so many unknowns, and all we have to do is solve for them. Well, that's in your textbook, okay, and you now have to solve for them, and there's a solution of a set of equations. So I had f of x1 x2, 0.25 x1 squared plus x2 squared. This is my old example from the appendix of the economic dispatch chapter 2. And then g of x1, x2, that's an equality constraint. 5 minus x1 minus x2 equals 0. And then h of x1, x2 is x1 plus 0.2 x2 minus 3 less than or equal to 0. So if you go back to that appendix, you can see the picture of it and so forth. And to do this interior point, so then we're going to say minimize f of x1, x2. I'm gonna drop the equality constraint and solve. I did this in the book, but in any event, we set this up and we say, well, here's our Lagrangian function is 0.25 x1 squared plus x2 squared minus mu to the k ln. There's only one s, so I don't need a summation sign. Plus, and I'm gonna drop this function here. So then I'm just gonna say that my function here, I was gonna turn this around, minus x1 minus 0.2 x2 plus 3 plus s. So there's the and now we take our partial derivatives, and we form that matrix. And there's actually a computer code that was written by one of my students several years ago and presented in class, and I was able to get the code. I'm going to give you that code, and I probably will give you a slightly different problem to try. What you'll see is that this solves remarkably quickly. And the interesting thing is that you just keep adjusting mu to force solution. Now you say, well, why don't we just put the right value for mu in at the start? It's an iterative process, and so you start mu out typically like a value of 1. That's a 1 is always a nice kind of neutral number to stick in there, and then you get a solution, and then you use that solution as the starting point for the next. Remember, Newton's method has to have a starting point. So you put a value of mu in there, and that gives you a starting point. It gives you the first point, and then you go and you start increasing the value of mu, and it forces the solution to converge in a not too many steps, maybe 3-4 steps, to the optimum. But you need that initial mu to get a first crack at the problem, so to speak. And there's various strategies for figuring out what mu is, and so we're going to have you do some very quick optimization problems with the interior point and with the interior point code. I will assign that problem probably Monday. So we're going to have a homework problem to solve. Interior point OPF, not OPF, but just a problem. I do have some code that was developed around interior point. I'm chuckling here because some students developed the code, and then in a course I gave about a year and a half ago, I gave that code to some other students, and I said, make this work, because the first set of code didn't work, and they did. They said they did, and they wrote a report. If I can dig that up, there is an optimal power flow written with interior point methodology. Interior point and iterative LP are the two methodologies of solving AC OPF. Now, so let me kind of list these. So we have iterative LP OPF. We have interior point OPF. And then we have, along came this independent company, I'll say 5-6 years ago, although they were in business for a lot longer than that, but they got bought by IBM. They were called Cplex. And it became IBM's product. And Cplex, you just put nonlinear equations in and say go, and it just solves it. A lot of what happens inside of Cplex is just unknown to the user. But Cplex's claim to fame really is that it solves not only nonlinear optimization problems, but optimization problems with integers. So you can set it up, and its ultimate claim to fame is to have a unit commitment with each commitment tried solves a security constrained OPF. And you know that unit commitment is 1-0 programming. It's 1-0 programming. And it's very hard. It is very, very hard. There is now a 1-0 programming for linear program as an option in MATLAB. But Cplex is a huge product. The University of Minnesota actually licenses it. At least they did, and I've had students use it. So that's the other means of solving these things, and it is the choice. This is generally the choice of your in the United States of the ISOs, because it's as close to the optimum that you can get with integer variables and so on and so forth. Places like the California ISO, for example, originally did not use that. They used a Lagrange relaxation unit commitment with some sort of SCOPF built into that. Their second rebuild of the California ISO, they went to Cplex, and because you want people to know that it is giving you a dispatch that's considered the optimum, the best that could ever be done. So I can't tell you the algorithms that are inside of it. It's an amazing company. If you can read a little bit about it. It was a company, I don't even know if they had a headquarters any place. They were all independent people that worked from offices, different parts of the world, and cooperated over the internet and created the code and tested it and so forth and so forth. And then eventually they got the code to work. And IBM has a good sense of what's going on in the business world, and they could see that here was a tool that companies would use and be willing to pay for. So IBM bought Cplex, bought the rights to it, and now it's an IBM product that they maintain and sell. Okay. Last of all, I want to talk about the relationship of LMP. Let's LMP. Okay, what is it? Remember our little two-bus system here, where we have a generator and a load on each bus, and here's 2, here's 1, here's LMP1 and LMP2. And LMP, as far as the load is concerned, is the cost of buying the next 1 megawatt of load. Okay. And so LMP I is equal to D cost, D P sub I, to buy the next 1 megawatt of load. And because of constraint, remember when we had no constraint on this line, then it was always equal to the cheapest cost of whatever segment was still available, and both of these had the same LMP. Once we had a constraint, then the next megawatt either comes from this generator or this, and the costs are different. And the LMP is used to allocate allocate costs to the loads. So loads pay at LMP. Okay, they pay. That's the amount they pay. That's the price they pay. And generators are paid at LMP. So if you have a generator and a load on the same bus, the load is paying the same amount per megawatt that the generator is being paid per megawatt to put power into the bus. Okay, now the first complexity that comes up then is, well, what about losses? And I'm going to develop the problem, and I did this. It took me. I wanted to explain it to my class, and this set of equations took me days to go through and to get it right. It's correct now, but it's difficult to do. I want you to think about, here is bus, here's the reference bus, and here's bus K. Okay. And the reference bus has a generator on it, and we're going to put in delta P ref, okay, and we're going to take out delta PK. And it will turn out that delta P REF is going to equal delta PK plus, and we're going to have a transmission system in here, and there's losses. So we're going to say then that it's minus dP loss dPK delta PK. Now, earlier in that section in the text, I make the argument that anytime that you increase the power on a generator, that the generator is pulling this out. It's negative, and that's why this negative number. You can read that in the text, the reasoning behind that. I do remember doing this many years ago before we finished this chapter in the book. This part of it, getting the SIGN correctly was difficult. So I said, okay, now then what is the cost? What is the LMP out here? Okay, so here's my total cost is the sum of the C over all the generators, PG. And I said, well, what is the delta cost? Delta T cost is then DC ref for the reference bus, DP ref delta P REF. So that's the change in cost if only the reference bus changes to add 1 megawatt to bus K. Okay, so again, I'm going to put this in red. I'm going to say add 1 megawatt here, and up here as I'm going to add megawatts to keep things balanced. Now I say that it's not 1 because of the losses. And if I add power here and the losses go up, then he puts out 1 plus a little extra. Okay, that's it. Now, part of the reason that this is a negative sign here is that if you add 1 megawatt here, then the delta P is minus 1 because you're increasing the draw from the bus. And this injection is considered negative because it's coming away from the bus. Remember that. As I said, that was one thing when we were writing that chapter that really got in the way, and until we worked that through. That's kind of a cheating way of saying I didn't know what I was doing until I figured that out. All right, so the LMP at K is the change in T cost, the total system cost, divided by PK. That's LMP. How much does the total system cost change for a delta PK? And that's going to equal D C at the reference bus, dP ref, times 1 minus dP loss dPk, like that. So we can say then, what is the better, this is loss here, OSS, loss. Then I'll expand this. This is DC, the cost of the reference bus, P ref, okay, minus, I'm going to flip it around and just say dP loss, dP ref, dC ref, dP ref. Well, this is the change in cost at the reference bus, and so we call this LMP at the reference bus. Same thing here, LMP at the reference bus. So we can say then that LMP at K is LMP reference minus dP loss dPk LMP at the reference bus. Now that's one of the fundamental results of this thinking, and it's a very important result. It says that whatever the cost at the reference bus, assuming it's a generator, which you normally would have it as a generator, then if you take the derivative of losses out at bus K, dP loss dPk, that incremental loss times the same thing gives you the LMP at K. Now, we haven't put any transmission lines in there, but this accounts for losses. This accounts for losses, and that is one of the fundamental results here. And anytime you do an optimal power flow on a transmission system with losses, and we'll see that in your homework whenever you run the ACOPF that I'm going to let you use, it results in different LMP, even without any constraints on lines. There's no constraints on lines. You get a different LMP for every bus because the loss effect is different around the system. The loss effect is different around the system. Now, the next one, we're going to need an effect. We're going to need I call it the A sub Li factor. And A sub Li is equal to the derivative of flow on line L with respect to a change of flow on P sub I. So let's come back and we'll draw our generator, our reference bus. And here's the load again with a delta PK. And now I have a transmission line. Line L in here with flow L. And this is at limit. So it's being held. Now so what I'm going to do now is I'm going to say, well, if I add my plus 1 megawatt to this load, or I take, I take more power out of the bus. Losses are going to change. So with the flow on this line. So with the flow on this line. I took 1 megawatt out of here. This flow will change. Well, I don't want it to change. I want it to stay at limit. Even though I'm changing the delta px. And the only way to do that is to add another generator, to bring another generator in here called J, and say, well, then the change in this load here of 1 megawatt causes a change in the losses, and it affects the flow on this line, and this generator will adjust to keep the flow constant, and of course I get a delta P ref here. So this is you have to start from that viewpoint. Now I want to tell you, if you have 2 lines, then you have to have 2 generators like this, and everything is done in matrices. It can be done. There are some IEEE papers on this, but my way of doing these things is to always try and do it the simplest way possible for the students, and then to start out with that. So we have a Lagrangian. We have C reference times P ref. Oh, and we have a Cj times Pj, and we have plus lambda times P load plus P loss minus P ref minus P J, and then I have my constraint, which I'm going to use mu for the line flow limit, and I'm going to say flow L minus flow L. This is its limit. So this is its limit, and now this constrains the line to stay at limit. Okay, now and we're going to assume that it's active constraint, so the mu is not 0. The Kuhn-Tucker-Karush conditions would force mu to be a non-zero if it's at limit. If it's not at limit, well, mu is 0, and then the whole problem becomes easier. You don't need bus J to do anything. And so you go through, and this, I'm going to let you go into the text and read this, because it's a long derivation. You end up having to account for the cost at the reference bus, the cost at bus J, and so on and so forth. And you have to know. Here's this system again. Here's J, and here's our line. We have to know how much does this have to go up or down, and in order to change the flow on this to compensate for the extra plus 1 megawatt of load over here. This one is going to compensate to force this back. Well, this generator doesn't have a 1-to-1 relationship unless it's basically this system is very simple. Generally, the change in this doesn't result in the same change on that, and so there's this A factor, and you end up with LMPK equals, again, LMP ref minus dP loss dP K LMP ref minus mu, that's the value of the constraints Lagrange multiplier, times ALK. Okay, and assuming that we don't have more than one constraint, so it's just minus that much. And what I did here, I ran my OPF, my iterative LP OPF, and it'll solve the problem like this. And this is in the book, but I'm just gonna go through this and say, well, at the solution, okay, this is lambda ref. So what we called lambda ref here is the LMP ref is equal to 12.506. This is the little 6-bus system in the textbook. And I have a program that will calculate the incremental losses at each bus of the system. Notice that they're not always positive. These are negative, these are positive. But these are our load buses down here. Okay, so that's good to remember. Load. 1, 2, and 3 are generator. Okay. And so here is this is the LMP calculated from that formula there. And I multiply this, I add to this the product of this times the LMP there and subtract it off. And I get these numbers like this. And when I ran the OPF, for example, let's take the biggest one is down here, 3.178. I got 3.183, 3.11, 3.114, 12.884, 12.892. It's not exact. And similarly for the generators, I got so I can calculate, and I just wanted to say, well, okay, does this formula give us a number that is reasonably close? And it is reasonably close to the value from the OPF. So this is I'll put this in big letters up here. That's the OPF numbers. These are the numbers from this formula here. Now, then I did it with a line 2,4 and 3,6 at limit. Okay, and here are the two A factors. These are the A factors in this. This is for 2,4. So this is the A factor for line 2,4, and this is the A factor for line 3,6. And here's my lambda for the reference bus, the incremental losses, and now here are the mu factors that it gets out of the optimal power flow. And I went all the way through and I calculated this from this formula that we developed before, and I compared it to the lambda values that we got from the OPF itself. One thing that I want to emphasize is that there are LMP values for each bus, and we showed a couple weeks ago that LMP is used for paying the generators and for billing the loads so that they pay for the power they use. There's also lambdas that come off of the constraints, the mu factors. The mu, if you study optimization, it simply says that's going to be the change in cost if I relax the constraint by, in our case, by 1 megawatt. And so if I relax the constraint, the mu factors, you notice here, and here, and here, this constraint here, if I were to relax that constraint by 1 megawatt, my cost would change by about 275. This one, it would only change by 1.038. So it's a very different mu. But the mu gives you a reading on how much each constraint is affecting the total cost of the problem. And that's just a little bit of an aside. You guys are master's degree students, most of you, some of you PhD students. I would strongly recommend a good optimization course where you could learn a lot more about interior point and LP and so forth. There used to be, that when I first started at the University of Minnesota, the computer science department also taught courses on optimization. I'm not sure they do anymore, but there is now a new group that's spun out of mechanical engineering, and it's called system engineering. There's also operations, industrial engineering operations research. Those two programs have very good courses, and our department has a course on optimization. So you've got your choice. You've got a choice of our own course in electrical computer engineering. You've got optimization course over in system engineering and industrial engineering operations research. There may be more in other departments, but those are the three that I know of in the engineering departments at the University of Minnesota. When I was a PhD candidate, I actually took an optimization course that was 2 semesters long, and we learned all the different optimization methods that were in use at that time. And that's where I learned LP, for example. So, I think I'm going to put this in with the notes. I think I'm going to end on that note, and I will be giving you some problems to do with the AC and with the DC OPF. I will be giving you problems on security constrained OPF and ask you to interpret results and so forth. And that will give you the background when we come back into this particular area, when we start talking about markets and how you devise a market, how you operate an open market, which depends on having a centralized security constrained OPF, and without which you could not operate an LMP market today. So we will do our little escape technique where if you have questions, of course, you can always ask me by email. But I am going to say this. There's a button on the host's display, leave meeting, and I say leave meeting. I say goodbye. So we'll see you next Tuesday. Though otherwise, if you're on the tour, I'll see you tomorrow.